So, in the old days, before the invention of balloons and before we had satellites, if you wanted to study what was happening in the, as you went up through the atmosphere, the only thing to do was climb up mountains. Now, most of the work initially was done in Europe, and this was the largest mountain in Europe is Mount Blanc. It's about 3 miles high, a little over 3 miles high. And so, in studying how the temperature varied as you went up through the atmosphere, they came up with the idea, or the measurements, that it was about 6.5 degrees centigrade per kilometre. Unfortunately, I'm a European, so I don't go into the Fahrenheit and miles. But I'll try to translate them when it's significant. Okay, so next slide. So we had ground-based measurements, and then we had the satellites, which were introduced in the late 50s, early 60s, and that gave us measurements from the top down. But if we go to the next slide, if you really want to see what's happening in the atmosphere itself, you have to actually go up through the atmosphere. So we really didn't get much data on that until the invention of balloons. And there was so I'm going to be dealing with the actual balloon data. We've come on a long way from that type of balloon, so go to the next slide. As a result of the studying of the different types of balloons, by 1972, we came up with this particular behavior of the atmosphere. So the balloons, when they are released, go up to about 35 kilometers, which is about 20-something miles. And again, as we found with the measurements on mountains, the temperature seems to drop off. Then it's proposed that there was a travel pause, and then so on. But the actual balloons go up to about this height, and that's 99% of the actual data. So, oh yes, sorry. This is just the altitude in miles, or kilometers rather, and this is the mean temperature. So what you see here, by the way, the temperature here that I'm using is the scientific absolute temperature. So to give you that 0 degrees centigrade is freezing point of ice. It's 273.15 if you're looking in degrees Kelvin, and if you're looking in degrees Fahrenheit, that would be 32 Fahrenheit. So, but there you can see this is the warmest bit. It gets colder, then the temperature stays in, then it actually starts getting hotter and so on. So next slide. So there's if you looked at the temperature there, when the temperature was dropping off, when they started using balloons, they suddenly found that around 10 miles or 10 or 11 kilometers up, the temperature, instead of dropping off, started to increase or stay the same or increase. And the explanation for this, they discovered the tropopause at about the same time as they detected ozone in the atmosphere. And so the explanation for the change in temperature, not dropping off and staying constant, was maybe it had something to do with the ozone absorbing UV light, which is turned into heat, and this was heating up the upper sections of the atmosphere, and that's why it stopped cooling as you went up. And the reason it cools as you go up is that in order to lift the gas up into the atmosphere, you have to work against gravity, and that gravity takes the energy out of the air, and that's why it gets colder as you go up. And then the question was, why did it stop getting colder? Because you're still going up through the atmosphere, and gravity doesn't go away. So the proposal was that it must be getting heat from the UV light being absorbed by the ozone. So the thing is, that hypothesis has been around for the last 90 years, and nobody has tested it to see if it's true. So we said, we have to start looking at these assumptions that are being used. So we said, can the weather balloon data test this hypothesis? And the answer is it can. So go to the next slide. So just here to give you what a weather balloon does, it travels up, it's released, has a little package of instruments here on it that measure the temperature, the pressure, and so on. And as it goes up through the atmosphere, it's filled with hydrogen or helium, and when it gets to about 35 degrees, or 35 kilometers, it bursts. But meanwhile, there's a little radio transmitter in it that is sending back the temperature, pressure at all the different regions as it goes up. So the next slide will show you, this is the sort of data you get back. So you have here the temperature at the different levels, the pressure at the different readings. You also have the amount of water, the direction of the wind and the strength of the wind and so on. So there is enough. Now this isn't the full radio sound. It actually is about 3 times the length of that. And another thing about the songs is there's an obligation on the people sending up these balloons to take certain mandated pressures. In other words, they must take a reading at each of these steps, which is useful as we'll see later on. So besides all of the ones in between, they also are obliged to take these. I've just underlined a few of the first few of the mandated ones here so that you can see them. So the next slide. So what this slide is showing you is what we can do with this. So the first thing is we can plot the temperature as a function of pressure. And this particular, we just gave this talk in Tucson there last week, so these measurements were prepared for Tucson. I didn't have time to prepare ones for here. But what you're looking at here is as you go up through the atmosphere, this was taken in January of this year in Tucson, the temperature drops off, and then this is the start of the tropical stratosphere. And so the next, this is the same. So what I'm doing here is I'm just showing you these two, the January and the July winter, summer temperatures for Tucson. And now, if you go to the next slide, I'll just take this particular one here, and instead of having it in the normal PV general gas law equation that you normally see, I'm going to represent this data using the molar density format. So if you look at that, suddenly these weird contractions or behaviors of the gas become very linear, and you just have 2 straight lines. Now, to a scientist, a straight line is like covering gold dust. It's easy to work with. So, next slide. These aren't just random or quasi-straight lines. If you look here, there's the blue line. These little circles are the actual measured data. And if you look in science, you do, if you want to test how good a line fits, it's called a linear regression. And a linear regression of 1 means it's a perfect straight line. A linear regression of 0 means there's no linear component at all. So you can see the correlations there are quite good. Next slide. That one that I just showed you was the winter, or was the one taken in the evening in the winter. This is one, the summer one. And what we find is, in this particular case, there's 3 straight lines, one down here in the boundary there, and we'll see what causes that shortly. Next slide. The thing that's interesting is, I've just took 2 there, but in case you think I'm cherry picking, I'm not. All 20 million radio balloon songs that have been sent up for the last 70 years, 20 million of them, they all show this 2 or 3 straight line behavior when you plot in the molar density. So, the next slide. What I've done is I just took Tucson for last year, and I plotted every single radio sound. I put it in the form of video. Could you just press that to get the video going? I didn't bother with the difference between the day and night ones down here at the bottom, so I've just been concentrating on the top. The thing to take out of it is the way this boundary between the 2 straight lines moves up and down, up and down. So that line there represents where the 2 lines intersect. And if you look at the top, you can see it jumps up and down by maybe 10-20% of the atmosphere in just the space of a few hours. Okay, so to show the significance of all of this, I just want to rotate this graph around here and put the molar density here and the pressure along the bottom and the ground one on the other side there. The reason I do this is that as a chemist, next slide. As a chemist, when we're looking at molar density, we can use it to find out properties of chemistry. We normally put it in this line there. Okay, yeah. So, what I've done here is I've taken the day and night temperature. In other words, one of the 2 sloped ones and one of the 3 sloped ones. And so this was for the 1st of January of this year in Tucson, both at 7:40 in the morning and 7:40 in the evening. And what you'll notice here is that at the ground level, during the day, it heats up. And that's the red ones today. But the slope becomes less for the red one. So if you heat up a gas, the slope of the molar density is less. If you cool down the gas, the slope is higher. Because the slope actually has got to do with how easy it is to compress a gas. And according to Charles's law, if you put energy into the system, it's harder to compress the gas, so the slope becomes less. So that is what's happening here. But if you go back for a minute, I just want you to note the slope here. And I'll explain now. We'll go on to the next one. This is showing the exact same thing in a different way. What I'm doing is I'm looking at the whole summer temperature. The whole air is warmer than the winter temperature, and you can see the slope for the warmer summer one is lower than the slope for the colder, higher one. To show that this isn't unusual, what I've plotted here is the lower 1,000, the ground temperature. You can see it's sawtooths up and down, day, night, and as you go up in the atmosphere, it gets less and less. So that by the time you get up to midway up the atmosphere, you can't see any daylight pattern at all. So, next slide. So, going back to this, what I want to say is, look at this slope here. So, according to Charles's law, if you add heat into a gas, it becomes harder to compress, and the slope of the molar density versus pressure gets smaller. In the stratosphere here, where the tropic pause occurs, we find that the slope gets bigger. So that's not what you would expect if you were heating the gas. It's the dead opposite. So this is the first time that the ozone heating hypothesis has been tested. Using this molar density, nobody had ever thought to do it this way before. And what we're finding is that the gas at the tropopause becomes more compressible. The slope is bigger. You can see it takes less of a pressure to give a bigger change in molar density. Now this is astounding, because that means we cannot be changing the temperature by adding heat into it. Because if it was, the slope would be going that way, the same as it was for the other places where we added heat. So what we conclude from this is that the ozone heating hypothesis fails. Go on to the next slide. However, this is what is interesting, is just as we came along and found that we could turn the temperature profile into a molar density profile, similarly, if we use those straight lines, we can calculate the actual pressure from the molar density, and when we do that, we find that we can get the lower boundary layer is done by one slope. The other one here is the next one, and the top one there. So those 3 straight lines that I showed for the summer temperature, this is the same one for the daytime. We find that we can represent each of these regions by an equation of state. And this is important, very important, because an equation of state, if you can represent a region of the atmosphere by a single equation of state, that means that that section of the atmosphere is in what we call thermodynamic equilibrium. And so what we find is that for the daylight, you need a separate equation of state for the boundary layer, and at night you don't. And so what that means is that these regions are all in thermodynamic equilibrium. And this is, say, the next slide. Now, once we've now determined that the ozone heating hypothesis, which people have believed for the last 90 years, is not valid, it's not working because it does the wrong thing to the molar density, we can then start looking at all of the other things where it went wrong. This is the standard atmosphere that was produced by NASA in 1972. So you can see, if you look at it, the temperature in the polar regions where you get the most amount of sunlight is colder than the temperatures in the polar winters when there is absolutely no sunlight at all. So you can see here again is another grounds on which the ozone heating hypothesis failed. Nobody bothered paying much heed to it. They just assumed that somehow or other it's got to do with with heating. But we're now saying on all of these grounds here, the molar heating or the UV heating hypothesis as the cause of the tropopause doesn't work. So we have to dismiss it. So next slide. So, must be scrapped. We need a new hypothesis. Next slide. What we looked at is, could you go back to the slide where I had the ideal gas law?
No.
No? Okay.
Keep going,
I know he's nearly there.
Nearly there, don't worry, Willie.
Okay.
You get your chance to speak again.
I know.
He wants to hug all the time. Okay, the one before this, oh no, that one. If you kept pressure the same and the volume the same,
slide projector hat.
if you added heat in, you would raise up the temperature. But if you don't add in heat, but if instead you were to reduce the number of molecules in a given gas, that would mean that the temperature would have to rise again. So what I'm saying is there is another reason why you could get a rise in temperature, and that's if you got a reduction in the amount of molecules that were in the region. So if you go back to the very back down to the
That one.
yeah, there. What we found was that if some of the molecules were to coalesce into a bigger molecule, that would reduce the number of molecules, even though you'd have the same weight, the same mass, and the same chemical composition. So it seemed like a bold sort of thing, but in actual fact, we did a number of other tests, but I'll just go on I'll come back to that later. But we have published this, and you can see it all in one of our papers. Right, go on. Let's go on to the next bit. How am I doing?
I think good. No,
Right. Okay. Here is something that's very interesting. This was taken. This is for May in Germany. The reason I take the one in Germany is that they have very good records, and they do 4 balloons every day, one every 6 hours. So each of the sawtooth things at ground level is actually 4 points. So if you look here, you can see the sawtooth, but as you go up through the atmosphere, very soon you lose the day-night behavior. So you can see a strong correlation here between the 500 and 400 one. But the interesting thing is, if you go up above the tropopause, that's this region here, it's anti-correlated. In other words, when one goes up, the other goes down. Now, we can explain this phenomenon, which, by the way, nobody has seen this before because nobody ever thought to plot data in this particular way. It's strange with all this data that nobody ever thought to look at it. But what's interesting here is in terms of the change, it doesn't matter what's causing the gas to become more compressible, whether my hypothesis that it's van der Waals molecules of oxygen, it doesn't matter, we don't care. What we know is that it becomes more compressible. So if that compressible area moves down, which you can see it moves up and down, you saw the speed at which it moved in the video. If it moves down, that means the gas becomes more compressible at a lower level, and you're creating a partial vacuum, because it'll occupy a smaller pace if it's at the same pressure, because it's more compressible. If you create a partial vacuum, that will suck air upwards into this vacuum and suck air downwards into the vacuum. And if you suck air upwards, you're raising it up, it'll get cooler. or if you pull it downwards, it'll get energy from the gravitational field and become warmer. So because this boundary layer moves up and down, we're creating compression, expansion. And so you can see here, this is exactly what we're getting. This is where the boundary layer occurs. The air above it, if it's pulled down, would get warmer, and the air below, if it's pulled up, would get colder. And so it now appears, and we have found that this happens in every station all over the world. And what we have found is that the temperature moves up and down, like a concertina. And so this is all absolutely new. Right, go on. So what we're saying is the models and everything else that people have been doing, the models assume that the atmosphere, the different sections, are thermodynamically isolated from each other. And that, so when they do their calculations, they will calculate these different values for as if the atmosphere was only in local thermodynamic equilibrium. That means that this one is isolated from this one and so on. What our data has shown is that this is totally false. The atmosphere from ground to the stratosphere behaves as a single unit. It's true it can expand in and out, but it does, the whole behavior is as if the atmosphere is just one continuous piece in thermodynamic equilibrium. And so we're now suggesting that if you want to do a proper model, get rid of this so-called thermodynamic isolated phenomenon and start using a continuous spectrum. So I think that's it.
Okay, that's it. No, that's it.
Okay.